Complaining. I'll say there's no. Good. I'll report to him that it went well. There's a question we have to address. So remember, I changed the date of the midterm, and that sort of changed everything around. And so in the original plan, I had planned that this was the last lecture before spring break, just because we're going to have just had the midterm. I figured you needed time off, but we're not going to have the midterm till later. So according to the web, Wednesday there's no class. It's the beginning of spring break. But since we didn't have the midterm, I don't know if you really want to take Wednesday off or want to have class. Some of you may have made plans. I don't know. Does anybody have any strong feelings? Who would like to start spring break on Wednesday?
Thursday. You mean Thursday?
Sorry, Thursday. In other words, skip class Thursday. No, it's okay. You can be honest. It's all right. You don't hurt my feelings. Who wants to have class Thursday?
Have a review class, a new class. A review in class.
A review?
I mean, like new stuff, right?
It'll be new stuff. I got a kind of ambiguous vote there. So who wants class Thursday? Okay. I'm afraid I should have changed the schedule earlier, I guess, right? All right, in that case, the majority wins here, so it looks like there'll be no class Thursday, and you can just have an extended spring break. And then we'll continue after spring break. All right? Any questions about anything then before we start? All right, what I want to do today is finish the non-parametric Bayes, and then the next topic we're going to do, we'll see if we get to it today, is clustering. I'm going to do quite a bit of clustering, I think. And then after that, I think we're going to do graphical models. So today we want to talk about the theoretical properties of these non-parametric Bayesian things. I think this is quite interesting because if for nothing else, it's an example of where non-parametric inference and parametric inference, there's really quite a distinction. So the questions we want to address is, if I do non-parametric Bayesian inference, what does that mean? I'm going to put a prior on a space of functions. Could be density functions, CDFs, could be regression functions. And then we get a posterior distribution, which would be, say, the probability that the function's in A given the data. So I'm calling that pi sub n of A. What are the properties of that? So we want to talk about consistency, rates of convergence, and confidence levels. Now, the first thing I want to mention is something called Dub's theorem, a very famous theorem which is often cited. Dub's theorem seems to tell you that the posterior is always consistent. It's often cited that way, but it's actually a little bit misleading. Dub was a very famous probabilist, by the way. So here's how Dub's theorem works. First of all, you notice that, let's go back to parametric inference. If I have a prior on theta, and if I have a model, P of y given theta, then that defines a marginal distribution for y, right? That's the distribution for y before you see the data, is the probability of y given theta times the probability of theta averaged over theta. So in a sense, you have a prior over the data before you even see the data in Bayesian inference, because you can average over the unknown theta. What Dub's theorem says is no matter what, essentially no matter what the prior is and no matter how non-parametric it is, this is always consistent in the following sense, that if I look at pi n of A, and if I think about the true density, let's call it F0, let's talk about density estimation, either A contains F0 or it doesn't. So you would like this posterior probability to go to 1 or 0. And what this says is this, in fact, equals 1 or 0. That is, equals the indicator function in the limit. That the limit, as n goes to infinity, this equals this. But the probability that this happens is 1. So this looks like, what this is saying is that the posterior, if I take any set A, let's say it contains the true density, and I ask, what's the posterior probability? That's converging to 1 with probability 1. So that seems to say it's doing the right thing. But the reason why that's not a very good result is this is with respect to this distribution mu, which is defined with respect to the prior distribution. So it's a little bit misleading because I would call this, in philosophy, they call this solipsism, right? It's like if solipsists believe there's no universe, there's only yourself, right? This is with respect to the prior. So to give you an example, if I were to put a point mass, suppose I was estimating a mean of a normal and I put a point mass at 0, then what's the posterior going to be? That's your prior. What's the posterior going to be? Point mass at 0, no matter what the data are. Now, you might say, well, how doesn't that violate Doomb's theorem? Doomb's theorem says we're going to be consistent with probability 1. Because if theta was over here, obviously the posterior is inconsistent. It's concentrating here, and here's the truth. The reason why that doesn't violate Doomb's theorem is because Doomb's theorem is with respect to the distribution induced by the prior. According to the prior, there's no chance that theta can be over here. So there's really only one possible theta according to the prior. And this measure mu is actually only considering observations that are generated from things with a mean of 0. In other words, this is happening with probability 1 with respect to mu, but there are sets outside the set of probability 1 that could be huge sets. Just because a set does not have probability 1 under the prior, it could still be a very large set, and that's especially true in non-parametric inference where we're dealing with infinite classes. So this theorem, Doomb's theorem, for a while was used as a sort of justification for consistency, but I think it's pretty much rejected now, that it's not really capturing what we want in terms of consistency. Okay. So, however, there was quite a bit of confusion, I would say, in the 80s about then, well, what do we mean by consistency, and is it consistent? When is it consistent? And the answer is consistency is actually fairly easy to achieve. So I'm looking at theorem 6 at the bottom of page 14. Yes?
Real quick, I'm struggling to understand the notation here. Pi n of A is
The posterior. I just wrote that for short. I didn't write the given y1 to yn. Yeah, that was just a shortcut. Here's what happens. I'm going to actually simplify this theorem a little bit. Suppose, again, that this is the true density f0. And it turns out that in Bayesian inference, Kullback-Leibler distance turns out to play a very important role. Because I'm going to consider a Kullback-Leibler neighborhood of the true density. I'm going to consider, I'll call it k delta, the set of all g's such that the Kullback-Leibler distance between f0 and g is less than delta. Remember that kfg is just this. And roughly speaking, here is the sufficient condition for getting a consistent posterior distribution. Suppose that I look at every Kullback-Leibler neighborhood. Let me draw my blob bigger. You take the true density and put a Kullback-Leibler neighborhood, all the densities that are within a distance, delta. And suppose that whenever delta is positive, we're putting positive prior mass on that neighborhood. So we're putting positive prior mass on every Kullback-Leibler neighborhood of density f0. Then, if I draw data from this density, if y1 to yn are drawn from f0, what we conclude is that the posterior probability remember, I'm writing, well, let me write it out. The posterior probability, I'll write it like this. This is a number, but if we're now standing back and evaluating it in terms of its properties from the frequentist point of view, this is really a random variable. I've given you some data, you've computed the posterior probability, you get a number. But if I gave you another data set, you'd get another number. So think of it as a random variable. This is going to be a neighborhood around F0, but it's not a Kullback-Leibler neighborhood. I'll explain in a minute. It's a different neighborhood. And this converges to 1 in probability. And what is this? This is actually I think I used a Hellinger neighborhood. Yeah, this one's less familiar. Let me explain what this is. This is the set of all g's such that this distance, and I've mentioned this distance maybe once or twice throughout, maybe in 705, but not very much. What is this? This is like the L2 distance between G and F, but using the square root of the density instead of the density itself. It turns out, for certain technical reasons, that's actually a much more natural metric to use. This is called the Hellinger distance. So this is just another distance between densities, or between distributions. And let's parse this theorem, because it's a little bit confusing because I'm using two different neighborhoods. If I put positive probability in every Kullback-Leibler neighborhood, then the following is true. For any epsilon, doesn't matter what, Hellinger neighborhood around the truth, the posterior probability of that will go to 1. In that sense, the posterior is consistent. And it might seem odd. Why am I using two different distances? You might say, why for the prior am I using Kullback-Leibler, but I'm expressing the notion of consistency in Hellinger distance? And the reason for that is fairly technical. It wouldn't be true if I used the same distance in both places, it turns out. So that it's interesting, because what it's showing you is that there's some subtleties about which distances to use. But the important thing is it's a fairly weak condition. It's easy to construct non-parametric priors. Most of the non-parametric priors people use do satisfy this property. Okay? And so in some sense, the posterior is concentrating around the truth. And so that's a positive result about consistency. I realize, again, that the fact that there's two different metrics might be a little bit confusing, but that comes really from the proof. Yes?
Do we have any requirements on the value of delta?
This has to hold for every delta.
So that can be large.
Well, large isn't a problem. We want the probability to be positive. The difficulty is when it gets small. So it has to be positive. This has to be positive for every delta bigger than 0. That's just like in the parametric case. If this is the true value of the density, one of the conditions you need of the parameter, one of the conditions you need is simply that the prior has to put positive mass around every neighborhood of theta 0. So it's really just saying the same thing. It's really a local condition. So the upshot is that there are conditions that guarantee consistency, and the condition is actually fairly weak. Is this necessary? It's sufficient. That's a good question. I don't think it's necessary, actually. But I'm not 100% sure about that. I haven't thought about that in a while. So I toyed with now. I spent some time thinking, should I go through an outline of the proof? Because the advantage of that is it's actually, if we wave our hands a bit, it's not too difficult, the proof. And it would give you some insight about what's going on here. On the other hand, it's going to take time. So I've been flipping a coin in my head. And I didn't put it in the notes. I just put some notes down here in my handwritten notes. Yeah, I'm always undecided about proofs because they can be very revealing, but I know people can get bored when I do them. So I was really trying to decide whether to, I'm still flipping a coin. It's still spinning. It hasn't settled down to heads or tails. Let's put it off for now, and maybe if there's time at the end of the class, maybe I'll go through it. Because the proof is not difficult, and it reveals why you need these two different metrics and so on. But an important takeaway, by the way, is that something common between Bayes and maximum likelihood is, you notice how Kullback-Leibler often pops up. Remember when we're talking about maximum likelihood, the Kullback-Leibler distance naturally pops up. It just seems to be a quantity that naturally pops up when you're using likelihood-based methods or Bayesian methods. All right, so consistency, in some sense, I'll come back to consistency actually. It's not as simple as I just made it out to be. But there are priors that give you consistent posteriors for large sets of densities. But now, let's talk a little bit about rates of convergence. Suppose you were doing, like estimating, a density or a regression function. We'd also like to know, for that problem, is the posterior converging? Is it concentrating around the true function at the minimax rate? And it turns out things get a bit trickier in that case. So let me give you this is example 7 at the top of page 15. So we're going to consider the following problem. This is the problem of estimating infinitely many normal means. So let me explain. Yi has mean theta I, and then these epsilons are just independent standard normals, and there's a 1 over root n, and there's infinitely many of these. Now, why would this ever come up? Well, it's actually what you're doing when you're doing regression, right? Because if I took regression, and if I took the regression function and expanded it in some basis, then estimating the regression function, we could recast that as a problem of estimating these infinitely many coefficients. And we would come up with some sort of estimate somehow, like using basis functions like we're doing. And typically those would be at least approximately normal with mean theta j and some variance, say sigma squared over n. So you could rewrite non-parametric regression as the problem of estimating infinitely many means that are approximately normal and with a standard deviation of 1 over root n. So this many normal means problem is often used as a way to investigate properties of things just because it's an easier model, but it actually does correspond in some mathematical sense to non-parametric regression. In fact, there are papers that make this very formal. There are papers that show that any estimator here can give you an estimator for non-parametric regression, and conversely, any non-parametric regression can be formally converted into a many normal means problem. Okay, but this is just a bit easier to work with. And the parameter now, instead of being a function, is just a sequence of real numbers. So that just makes understanding what's going on a bit easier. And if I told you the regression function is in a, say, a Sobolev space, that corresponds to a restriction on the thetas, which you dealt with actually in a homework assignment. I'm going to assume that the parameter, the set of thetas, is the set of infinite sequences that satisfy this condition. This is exactly like saying, if I was in the function world, it's like saying it has p smooth derivatives. This is just the sequence version of saying that. So think of p as a smoothness index. All right. Now here's an interesting thing. Suppose you wanted to do Bayesian inference. So suppose I gave you an infinite sequence of y's. If that bothers you, I'll give you 1,000,000 instead of infinitely many. It'll be pretty much the same thing. And I ask you, estimate these theta i's. And I'm telling you there's this restriction. How are we going to do Bayesian inference? Well, I think the easiest thing to do would be to put some sort of simple prior on each theta I. So what prior, give me a prior. So let's suppose I'll take independent priors on each theta. That'll make it easier. So what anybody have a prior they want to put if you wanted to actually compute these things? What would come to mind? Normal. That's a good idea. How about the mean? No, you can't use the data. That's cheating. It's the prior. 0. 0 is a good one. Now, the tricky part is the variance. We're expecting these thetas to get smaller and smaller and smaller. That's what this condition is saying. So people typically take a prior, which let's call it tau I squared. Okay. Where these are going to be chosen somehow. All right. And it turns out that the one that sort of works and gives you consistent posteriors and so on is to take tau I squared to be equal to, let's call it, what did I call it here? 1 over I, let's just say polynomial. We'll call it 1 over I to the 2q. They're falling off polynomially. That turns out to be, in some sense, the right thing to do to get a good posterior that's consistent and so on. And so you can see Bayesian inference, even though we're dealing with an infinite dimensional problem, is pretty easy because you just now take, for every theta I, you have a normal prior and a normal likelihood. You multiply them, you get a posterior. It's very simple. And it separates. You can deal with each parameter separately. So you have you have infinitely many of them, but each one's a simple thing. And the posterior is also going to be normal. And it makes it very easy to investigate the properties of the posterior distribution. The space is a bit weird, right? It's on this infinite set of sequences. But nonetheless, we can do that. Now, it's not hard then. Here's a good exercise. Maybe we'll put this on a homework to compute the posterior mean. It's trivial, actually. And once you have the posterior mean, you have an estimator. And you can forget that it came from Bayesian inference. I'm just handing you an estimator. And you can ask what's its bias, what's its variance, what's the mean squared error. So it's very easy to investigate things like the rate of convergence and consistency and so on. But here's an interesting thing that happens. Did I not include that? Yeah. Okay. So we would like to get a couple of properties from this thing. All right. If I compute the posterior mean, which again is very simple, so the mean of each theta I, it only depends on yi. You can write that down. It's a normal calculation. You have an estimator, compute the bias and variance. Now you can just ask yourself, when I compute the mean squared error, what choice of q makes the posterior mean converge at the minimax rate? We know the minimax rate. And it's easy to solve for it. I'll tell you the answer. It's unique. This is it. If you really are keen on this, you can do the calculation. It's not difficult. But if not, just you can trust me. And this gives you the exact choice of prior now, such that the posterior mean, so our theta hat, which is an infinite sequence,
What is the means of the Bayes estimator attains the optimal rate?
well, I have an estimator, and I can ask what's the mean squared error of the estimator. And I want to know, does that mean squared error go to 0 at the same rate at the minimax rate for this problem? Okay, so it seems like we have we're sort of all set, right? There's only one problem with this. If I look at my set theta, now this is a little bit hard to draw. I always draw these sort of generic blobs to represent things. It's getting a bit harder because these spaces are infinite, but I'm going to let this be all sequences, if you can use your imagination. And this is the set theta. Okay? So this is to be all sequences. and this is the parameter space. We've now shown how to choose the prior in such a way to get the minimax estimator. There's only one weird thing about this. If I take this choice, and again, this is not a hard calculation, you'll now see that the prior puts mass 0 inside the parameter space. And in fact, that means that the posterior probability of the parameter space is 0. That's pretty weird. You might wonder if the posterior doesn't even put mass here, how is the mean converging at the optimal rate? Well, you can have a distribution that's outside here. When you take the mean could be still inside here. Right? If I take a distribution on a circle and take the mean, I could end up with something inside here. So we have a very interesting thing, which is that the posterior mean will be minimax. But the posterior itself is not concentrating at the minimax. The posterior is like staying away from the truth, which is pretty strange behavior.
So, and I presume that this is a consequence of the fact that we defined our prior over that whole space instead of restricting our prior just to...
If you restrict the prior to that space, you won't get the minimax rate anymore for the estimator.
Can't see why the posterior put 0 probability.
If the prior puts 0 probability, then so does the posterior, right?
Why does the prior put 0?
I actually did that calculation for you here. It's just Markov's inequality in equation 43. It's a very simple calculation. Now, I think this was a bit surprising to everybody when this was discovered. But, and I think we would agree this is kind of weird, right? This is not somehow the behavior you'd want. But this is the prior most people use. Those Gaussian process priors we talked about last week are basically this prior. If you really wanted to get a posterior which converges, which not only its mean converges at the right rate, but the whole posterior, its mass is converging at the right rate, the trick is you cannot use this simple type of prior. You need a much more complicated prior. And it's possible to construct them. I won't go into the details, but the standard priors people use don't suffice, as it turns out. So what's the point of all this? I just want you to be aware, and then by the way, I'm not saying you shouldn't use these things, but if you're going to use them, you should be aware of what their properties are, that's all. So you should be aware that these posteriors have some pretty strange, unexpected behavior. And it still might work well in some practical sense, but it's certainly unexpected, the behavior. Yeah.
So if you could just go into a little more detail about the relationship to the Gaussian process prior, because we have here all these independent, the prior factored over all of the things.
We've defined actually a Gaussian process because if I take this function and I write it this way, and I put normal, then I put a prior in this, and because the prior is a sum of infinitely many functions with random normal coefficients, that makes this a Gaussian process. That's actually a way of generating a Gaussian process prior.
But it's a pretty weird kernel, isn't it?
No? Actually, pretty much every Gaussian process you've ever seen can be written this way. This is called the Carhoon-Loave expansion of a Gaussian process. So all the Gaussian process priors people use, they can typically be expressed this way, even if they're not originally written that way. If you really wanted to get the minimax rate, I'll tell you how you do it, is instead of taking normals all the way out to infinity, you take normal priors all the way out to some number k. Then you take k itself to have a prior. So kind of like when we talked about mixtures of Gaussians. And it turns out that posterior will converge at the minimax rate and will have the contraction at the minimax rate. But it's much harder to compute the posterior, so it seems like people don't actually do that in practice. Okay. All right. Yeah, this is not saying you shouldn't use these things. They might still lead to useful answers, and they might be useful in many ways. I have no problem with that. But, you know, it's like if you're going to take a medication, you should read that label that comes with it so you know what the side effects are. I think if you're going to use statistical methods, you should understand what their properties are, and if they have certain behavior, you should understand what it is. I want a world where people at least think about the procedures they're using, and then if they want to use them, that's fine. What worries me is a lot of people, I think, use a lot of these things without even knowing about some of this kind of behavior. And so just being aware of it, that's the important thing. Yeah.
I'm sorry, just one last question. So, I mean, I'm curious about this picture, if this may be misleading. I mean, so we have here the theta is kind of like a compact ball.
Yeah, that's a little bit now we're getting to the limits of my drawing abilities.
Right.
I mean, because we're in infinite dimensions, but
I mean, I guess the question would be, is the space where the posterior actually has support, is it dense in big theta?
I think the answer is no. Yeah, that's a good question. Yeah, I'm not sure. I don't think it is, though. In fact, I'm pretty sure it's not. And more importantly, the posterior itself is not going to concentrate at the correct rate if you use that prior.
Is the previous process, does the Dirichlet process has this concentration behavior?
Does the Dirichlet process?
Yes.
Does it concentrate at the
Concentrate to the real.
Well, we're talking about a different estimation problem there, right? So that's a CDF. And there, what do we know about estimating a CDF? That the optimal rate for a CDF is 1 over root n, actually, right? Because we know, and yes, the Dirichlet process, in fact, does concentrate at rate 1 over root n.
No, I'm asking
Oh.
the condition in the theorem here. We use.
Oh, yes,
prior.
yes, Dirichlet processes satisfy that, yes. Yes, they do. So that's about consistency. Consistency, generally speaking, is pretty easy. Most of the priors people use in practice will satisfy those conditions. It's when you start to get to rates of convergence that it's not always the case that they will be minimax. You might not care if it converges at the minimax rate, right? This is just something to check. Okay, and the more strict thing now is to ask about coverage. Let's go back to parametric inference. If I compute a posterior distribution, suppose this is the posterior. And if I find a set AN whose posterior probability is 1 minus alpha. So I do get a prior, multiply by the likelihood to get the posterior. I find a set with posterior probability 95%. Now I want to ask, is it the case that this is also a frequentist confidence interval? If I computed the probability under the true theta, that thinking of AN now as just a set computed from the data that it traps, so this is now random, this is a frequentist calculation, is this equal to 1 minus alpha? So just back to the parametric world. If I compute a 95% Bayesian region, and now you hand it to someone, they don't know it's Bayesian, you're just giving them an interval, and they think, oh, that's a confidence interval, that's going to trap the true value 95% of the time. Is that true? Okay, it won't be exactly true, but generally speaking, it will be approximately true. So up to an error of order 1 over root n in most parametric problems, Bayesian 95% intervals are also approximately frequentist confidence intervals. We didn't talk much about that in 705, but this is true. This is sort of that Bayesian and frequentists tend to agree in a fixed finite dimensional setting. There's not a lot of practical difference. But now what happens in the non-parametric setting? Suppose we're in the non-parametric world, and I find a set of densities, let's say AN, such that the probability that F is in AN, given this, I can ask the same question. What is the frequentist probability, let's say, that, so under the true F, let's call it F0, is that going to be 95%, even approximately? And the answer is no. So this is quite different. This is typically I'm going to just say not equal to. Things behave much differently in infinite dimensions. In fact, the limit of this is often 0 in the frequentist sense. So the first paper I know about this is by Dennis Cox in 1993 in the Annals of Statistics. It's a hard paper to read. It's just a bunch of really complicated calculations. It's even hard to see the result in there, but he's basically getting 0. But there's a beautiful paper by David Friedman in 1999 in the Annals of Statistics, which uses the normal means model, because that's a much cleaner setting. And he just shows you that when you compute these posterior probabilities that are 95%, their frequentist coverage is typically close to 0. And it's not clear whether that's fixable. I suspect it's not fixable. So in the minimax situation, I said if you use a more complicated prior, you'll get back to minimax rate. I haven't seen a paper that has any sort of proof about whether you can find priors that give you the correct frequentist coverage in the non-parametric case. I suspect there aren't any, but I don't know if anybody's, I think it's an open question. And it may not be important. So, if you really want to use a Bayesian method, you could say it's okay if it doesn't have good frequentist coverage. Maybe we're asking the wrong question for the technique we're using. But it's just something to be aware of, that if you use this Bayesian machinery over and over and over again, and each time you compute a 95% Bayesian set for the true function, and you ask, how often am I actually trapping the true function? It won't be 95%. It could be very, very low. And so you have to decide, for yourself whether that's troubling or maybe that's not an important property you want to have. But the important thing, again, is to understand that they're different.
Maybe a simple question for equation 53, is that 0 or 0 factorial?
That's a 0 with an exclamation mark. Yeah, I generally don't use exclamation. I hate exclamation marks. So I don't know why I put one there. And that would make a difference there, actually. That was just supposed to be, boy, isn't it surprising that the coverage is going to 0 when the posterior probability is 95%. Again, the message I'm trying to get across here is just that they're different, and just to be aware of the difference. All right, I don't always succeed, but I'm trying to stay neutral. Tell you about frequentist methods, tell you about Bayesian methods, and I don't care which ones you use, but you should understand the difference. To me, that's the important thing. Okay. I'm not going through any of these theorems because they're very long and technical. There are references there, if you're interested to look at them. We're certainly not going to go through them in detail. But if you're interested, you should track down the references because the results are pretty interesting.
So I'm curious, maybe I'm mistaken, but so we've been looking at these confidence properties, right? So what about if we were just looking at like error, like how far, the soup of the distance between the...
Well, that's where the rate of convergence would come in. I would want the distance between the Bayes estimator and the truth to be going to 0, the distance to go to 0 at some optimal rate.
Right, but suppose it doesn't go to 0. I can still get small.
Yeah, but if you had a choice of an estimator which was not going to the distance between the estimator and truth was not going to 0, and one which is going to 0, presumably you'd want the one that's going to 0, right?
Maybe you're really easy to use one which gets close, but I know can't converge. But in most of these situations, there are ones that converge, right? So like a kernel density estimator, we know is going to converge distance between that and the truth to 0. Yeah. These are not typically, the other thing is these Bayes estimators are typically not easier than the frequentist estimators. They're actually more complicated to compute. Right. Yeah.
So why would someone who does use non-parametric Bayesian estimators argue for using them?
Well, I think there's a couple reasons. Some people find the Bayesian logic very compelling, and so they would argue that's more compelling than having good frequentist properties. That's not an argument I would make, but there are people who've thought about this a lot and do make that argument.
What is that Bayesian logic?
Well, that you want to start by expressing your beliefs with a prior, and then you want to do Bayes' rule and update it, and somehow that's a very consistent strategy for quantifying your knowledge about some problem. And that,
Well, what if I repeat the Bayes for many times? For example, I first assume a prior and got a posterior and use that as another prior and then repeat.
no, that's bad news. If you take the prior and get the posterior, now treat the posterior as a prior and get another posterior, you're going to get really weird things out. Yeah, even that's something that neither Bayesians or frequentists would like. It's not going to give you anything that makes sense.
If I change new data.
Oh, if you keep updating with new data, sure. But then again, you're asking basically what's happening asymptotically with the posterior, which is sort of what we're talking about, right? We want to know, is it converging eventually to something? Yeah. But to just finish the answer, there are situations where the Bayesian machinery gets used without the Bayesian philosophy. And in other words, it leads to procedures that seem to work well in practice. And so, for example, people will sometimes create classifiers. And in a classification situation, things are easier because forget all this theory. You can just check at the end, did it give me a good classification rate or not? And if it does, who cares whether it's Bayes or an SVM or whatever it is. The perfect example of this to me is document classification, where people take words in documents. They treat the words, each word, as a feature. You just basically count in every document how often does each word occur. That's the data. And you put fairly complicated models involving multinomials. The priors on tops of the multinomials are Dirichlet's, and typically there's another layer of Dirichlet's on top of that. And these things are representing word counts and topics and things like this. In the end, it's a fairly complicated Bayesian model. It's so high dimensional, it's basically non-parametric. These guys who do this, like Dave Bly and Mike Jordan, they don't believe the model or the prior. I mean, if you ask them, they'll say, no, of course, that's not a realistic description of reality. But at the end, what they get out is either some sort of clustering or classification of documents, and just in practice, in some practical sense, it does seem to often lead to very reasonable document clustering and document classification. So I would say that's kind of a pragmatic Bayesianism, is that there's no claim there that things are converging at some rate or anything like that, but it's a way of deriving a procedure that just seems empirically to work well in practice.
This would be similar to how we used it to get minimum estimates.
Yeah, so of course we did use it as a formal tool to derive minimax estimators, and there it was just a way, it was just a mathematical tool in that sense to get minimax estimators. Yeah, so when you say Bayes, it means different things to different people. There are some people who think of it as a very philosophical way of thinking about statistical inference and machine learning. For other people, it's just a tool to derive procedures and so on. It's a very wide spectrum. But again, I think you have to decide for yourself what tools to use. All I'm trying to do is make sure you're aware that, of course, whatever tool you use, they're going to have properties, and you always want to ask yourself, what are these properties, and am I happy with these properties? That's the real takeaway message here. Okay, now, let's see. Yeah, a couple more things. It is, one thing about this stuff is I have to say it is intellectually fascinating. At least I find it fascinating because it's full of unexpected surprises. And for years, like in the first half of the 1900s, there was these vigorous debates about Bayesian inference versus frequentist inference, but it was all kind of vacuous because who cares? You're talking about a one-parameter model with 10 observations or something like that. And that's the kind of, But now I think it's resurfaced because now in the world of doing non-parametric models or high-dimensional inference, all of a sudden these things actually matter in practice. You really get different answers. And so I think there's a sort of re-interest in all of these things, these issues these days. So I wanted to mention two more things that are kind of fun. Let's see how much time. I wanted to. This one really is just one of my favorite paradoxes that comes up when people compare Bayesian and frequentist inference. It's called the adventure in flatland. And then there's something called Friedman's theorem. Oh, maybe I'll do the adventure in flatland. Wouldn't that be fun? Okay, so it's just going to show you what can happen in a very non-technical way of seeing how you can get very different behavior in high-dimensional spaces. Yeah. Now I was thinking, should I do that, or should I do the proof of consistency, or should I do Friedman's theorem? I kind of realized I can do one of the three, and unless somebody has a strategy. Does anybody have a preference? Flatland. Okay. So flatland. Unfortunately, it's not in the notes, but I'm going to draw it on the board. This is, and here's how it goes. Is it in there? I don't think it's in there, right? No, okay. I'll do it on the board. Okay. This is actually from a series of papers by a statistician named Mervyn Stone in the 70s. And he wrote some very technical papers about the frequentist behavior of Bayesian procedures. And then one time he wrote a kind of funny paper that took the technical thing and expressed it in this very, very, more like telling a story. And it really illustrates what's going on. And it's about hunting for a treasure in flatland. Okay, so let me explain how this works. So you're in a city. All right, I'm going to draw a city for you. It's going to look like this. These are like buildings. All right, this is like these are city blocks. All right. All right. So here's what happens. I'm going to start right here at the corner of the city, and I've got a treasure. And I'm going to start wandering around randomly in this. But what's going to happen is I'm going to have a string follow me behind me. But it's not just a string, it's elastic. So what's going to happen, for example, is if I go here, then I go up here, then I go up here, then I go up here. So what you're going to see at this point is the string going all the way back, and here I am. However, if I decide to go backwards, the string disappears because it's elastic. Is that clear?
But then if you go down,
If I were to go down, now it would look like this.
there's some corrections. Some of the parts will go away. Some of
Only if I retrace.
okay.
Just retracing. Just like an elastic band. Right? If I go here,
The part where you wandered to up, that
yeah,
part is forever lost.
right, that's correct. You don't see that. Right, so all you see is this path. The ones when I went up and came down, I went to the right and came up, you don't see those. Okay? So I might wander around up here, go up here, whatever. Okay? Then at some point, I do this for a while, I get tired. And I think, okay, I'm going to bury the treasure. So let's say I put the treasure here. Let me make the city a bit bigger here. The treasure's there. Now I have just enough energy to take one more step. So what I do is I flip a four-sided coin, four-sided die, I guess. Four-sided die, which is either which has four sides: north, west, east, or south. And I take one more step. So for example, I might go here. Okay, now you come into the city. Of course, you don't know I put the treasure here. All you see is here I am, and here's my string. Your goal is to try to guess where the treasure is. Okay, but there's going to be two people. There's going to be Bob the Bayesian and Frank the frequentist. Okay. Let's call this, what did I call the path? Theta. So there's a parameter here, which is what did the path look like before I took that last step, right? If you knew that, you'd know where the treasure is, right? So that's like our parameter. All right, now, let's first of all do the Bayesian calculation and the frequentist calculation. Now, what's going on here is it's actually a high-dimensional space. The set of all paths is actually a very high-dimensional thing. And so this is where dimension comes into it. And there's some surprise. Even this simple little game has some surprises. I haven't said the estimate yet. Yeah, we're going to compare this one.
I'm sorry, so you know where the guy, Bob and Frank know where the guy who buried the treasure ended after he moved?
All we see is what I've just shown you on the board. He sees this path. They both just see this.
I'm not don't they know that the theta has to be one block away from there?
That's right. So what are the where could that's exactly right. So let's do the bit. Let's first of all compute the likelihood. So here's where I ended up. Okay, where could the treasure be if this is where the guy ended up? There's only 4 possible places, right? Here. I could have been here and then took a step. I could have been here and taken a step here. I could have been here, taken a step here, or I could have been here, which happens to be or taken. That's the only 4 possible places. Everybody agree? So let's call those north, south, west, and east. We can think of theta as being. Now let's compute the likelihood function. Here's where people get confused, so we have to be really careful. Remember, I don't know which one's the true state of nature. How do we compute the likelihood? The likelihood, you fix every possible value of theta, and then you say, if that was theta, what's the probability I would have gotten the data that I see? So let's go here. Suppose that, so here's this is west, south, north, east. Suppose the true value was west. Suppose I had ended up here. Remember what my last step was. My last step was to pick a random direction with equal probability and take a step. I have to keep expanding my city here. If this was really where I'd left off, I could have gone here, 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 or here. So what's the probability of the observed data that it's here? Yeah. That's a quarter, right? If I'm here and I choose one at random, this is a quarter. So the likelihood function that would be for west is a quarter. That's a quarter. But the same is true if I was at north. If I was at north, I could have gone here, 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 or here. Equal probability. So the observed data have probability 1/4. In fact, they all have probability 1/4. The likelihood is flat. Okay, that's fine. So that just says the 4 possible values have equal likelihood. Now I need to put a prior down. Let's start with the easiest possible thing, which is to put a flat prior. And we'll talk about that later. Then my prior times the likelihood is in fact the posterior. In fact, now you are looking at the posterior distribution. That's the posterior distribution. All right. Now, I have to, who did I call the Bayesian? Okay, good. Bob. Okay, I called him Bob in here. So, let me just stick with this. So Bob notices the following thing. I'm going to say, so there's 4 possible values. They each have posterior probability 1/4. Bob's going to pick one of these directions that extends the current value of the string. Okay. In fact, let's let him pick 3. I'm going to let Bob the Bayesian have 3 guesses. He's going to guess that the treasure is either at north, west, or south. Happens to be wrong in this case, but this is his guess. Okay. He's going to take all the directions that extend the string, and that's his guess. And that has probability 1/4, so that's 3/4. All right. So the probability, so I called this B2, which in this case, it might differ from what's in the notes. Unfortunately, I drew it differently in the notes. But anyway, it's west, south, north in this case. The posterior probability that the treasure is in this set B for Bob, given the data, which is the observed path, is 3/4. Bob's pretty happy. He's got a guess, and he's got pretty high posterior probability on it. Now, he starts to notice that Frank is laughing really hard. Frank is going to do the opposite of Bob. Frank's only going to, he's only going to take one guess, in fact, and it's going to be the one that retracts the string, which happens to be the right answer in this case, but we don't know in general if that's going to be the right case. Okay. But no matter, so Frank's, I called her Carla the classicalist in the note. So I should say, instead of Frank, it was Carla. So C C is B complement, in other words, or C in this case is going to be east. All right. But let's now ask from the frequentist point of view, if I repeated this game over and over, how often does Carla win the treasure? Bob's laughing at Carla. Bob says, that's a posterior probability of that set's very small. Well, let's think about Carla's strategy. Carla's strategy is she's always, no matter how the path comes out, she always looks and says, which direction contracts the string? So when is Carla going to be right? Carla's going to be right precisely when my last step extended the string. If my last step was an extension, then if she guesses that it was an extension and does a retraction, she's going to be right. How often? What's the chance that I do an extension on my last step? 3/4. Carla's actually going to win. In the frequentist sense, the probability that theta is in Carla's set is equal to 3/4 no matter what the path is.
So before when we were talking, when we said that the likelihood was flat, we weren't taking into account the path.
Sure we were. No matter what the path is, once you see the data, there's only 4 possible locations the treasure can be in. The path actually contains no extra information in terms of the posterior, except where it ended up.
What does this posterior mean? I mean, the Bob can only have one guess.
No, I'm going to be really generous to Bob. I'm letting him have a whole set. So if his set contains the truth, he gets the treasure. And he's 3/4 sure, so let's write the 2 statements down. From Bob's point of view, theta is in B given the path, the observed path, is 3/4. And he thinks that theta is in Carla's set is 1/4. There's nothing fishy here. I just took the likelihood multiplied by the prior, and that's just the arithmetic. But if I imagine myself repeating this experiment over and over again, we'll see that if we played this game, and it doesn't matter what theta is because this is for all theta, Carla's going to win 3/4 of the time, which means Bob's only going to win 1/4 of the time. This is just a stark example that posterior probability and frequency are different things. There's nothing wrong here, right? No one said posterior probability, which is a measure of belief, and frequency are the same thing.
But the only way you distinguish Bob and Frank are the fact that Bob chooses the option that extends the string.
Right. Yeah, although I'd put it a different way. Bob is using the posterior to construct his set, and he's picking a particular 75% posterior set. And Carla is asking, in the frequency sense, what's a good strategy? But this is just an example, again, of that posterior probabilities and frequency probabilities are very, very different creatures. And this is a high dimensional in the sense just that if you list out all the possible paths, I mean, it's a countable sequence. It's not a finite dimensional parametric problem. So, yeah.
From the frequentist perspective, what did the Bayesians do wrong?
Well, that's a good question. From the frequentist perspective, what did the Bayesian do wrong? What the Bayesian did wrong was they didn't ask what's the frequentist properties of their procedure. By the way, some people don't even believe this. So I always tell people, I've seen statisticians who, it shocks me that there are statisticians who don't know about these papers by Stone. But and I've seen very famous statisticians, I don't believe this. And so you can go and simulate this. Just go to your computer, have 2 people play with money. Have the computer go through this, leave a treasure. You guys don't see it. One of you can bet, take Bob's strategy. One of you can take Carla's strategy and then see, do $5 every shot and play it over and see who's, got the money at the end of the night. I mean, you can really do this and see what happens. Now, so the math I promise you is correct. There's nothing fishy about that. However, there is something you could object to, which is why should I use a flat prior? over all, essentially I'm putting a flat prior over all possible paths. It's an improper prior distribution. So there are two possible ways to fix this. One is I could say, well, I'll put a proper prior. Like maybe if I put a prior that puts higher probabilities near the starting area, and then the probabilities get smaller and smaller and smaller and smaller. That's not going to work so well because there will always be places in the tail. A proper prior, most of the parameter space is in the tail of the distribution. And you're going to have very, very poor, you're going to have very similar things happening now in the tail of the prior. So anytime you have a long string, in other words, you can check that the posterior is not going to, still not going to behave well. However, there is a way to pick a prior that mimics Carla's thing. And the trick here is if I construct a more complicated prior where I first put a prior on the length of the string. How long is the string going to be? That's a random variable at first before I see anything. I could put a prior on that, and then I can put a prior conditional on that. And it turns out if you construct it just right, the posterior will be very close to Carla's answer. So it is fixable.
But prior, it should not depend on the curve.
Well, that's a good question. What should the prior depend on? What I'm saying is you can formally construct a prior distribution which will approximate, so that the answer will approximate the frequentist answer. On the other hand, if you're only constructing a prior to try to copy the frequentist answer, then you could ask, why am I even doing Bayesian inference, right? What's the point of doing Bayesian inference in that case? So this is just stuff to think about. Yeah, I'm not giving you an answer. I'm just showing you that this is a fact. This is a fact about the real world. And you can simulate this. Yes?
Why isn't Bob allowed to have the same insight that he should put his prior on the only spot that could?
You can't look at the prior, you can't look at the data, right? The prior you construct before the process starts, or it's not a prior distribution. Yeah, so you can't.
So Frank is allowed to make his judgment based on the data. He's allowed to have a decision over that.
Well, they're both making a judgment based on the data. Frank has a very specific strategy. Bob, being the Bayesian, has a constraint, which is he has to do it by putting a prior down and now using Bayes' theorem. That's the constraint for doing Bayesian inference. Right. So the key here is that this is just, I think this is a fun problem. I like to talk about it just because I think people find it surprising. If you look at Stone's papers, you'll find this example. The earlier papers, it's going to be hard to see this. This is actually a group. There's a group. For those of you who've taken group theory, this is called the free group with two generators. And what's going on here has to do with distributions on groups. I mean, there's some actually fairly technical stuff happening here. And Stone's papers deal with this in much more interesting examples. This is kind of a toy problem. These same problems occur in real statistical problems when there's group symmetries. So again, if you're interested, go look at Stone's papers. Mervyn Stone wrote some really great papers. I guess I didn't give you these notes. Yeah, I don't know why I didn't do that. But I didn't think I'd get to this. It's just why I didn't mention this. At any rate, I'll tell you the reference. If you look up, if you're interested in seeing more of this, the guy is Mervyn Stone. I don't think there'll be many Mervyn Stones out there. If you look at Mervyn Stone, Bayesian inference, you'll find the papers if you're interested. Okay. What's the message in all this? It's just what I've said 1,000 times over and over again, which is you can do Bayesian inference, you can do frequentist, it doesn't matter, do whatever you like, but just don't confuse them. They're different. They're just two different things. Don't expect one to behave like the other. That's really what the message is. Okay. Any other questions? Okay, good. Then I think we're ready to move on. Although, I maybe have time to do the proof of consistency. I'm going to do, well, what the heck. We have a few minutes left. I'm going to show you an outline proof of what makes the posterior consistent. This is also not in the notes. So this is just extra information so you can kind of see what's going on. So imagine we're doing Bayesian density estimation. Here's the set of all densities, another one of my blobs. Here's the true density, let's say P0. And here's some set. Let's call, this set is B epsilon, the ball of size epsilon around there. What I want to do is compute I'm just going to compute the posterior probability outside that set, and I'm going to show you it goes to 0 as long as there's positive mass in the Kullback-Leibniz neighborhood. And so here's the calculation. Here we go. So the posterior probability of that set, well, actually, I want to look outside that set, given the data. Let's just do Bayes' theorem. So this is, and the likelihood is simply the product of the density. There's a prior on the density. And this is just the likelihood times the prior over the whole space. Okay? This is likelihood times prior, and this is over B complement and then over the whole space. Now what I'm going to do is just for convenience, I'm going to divide the top and the bottom by the product of the true density P0y. That doesn't change anything because it's on the top and the bottom. Okay? And now what I'm going to do is I'm going to look at this ratio. This looks like a likelihood ratio. And I'm computing it, I'm integrating it all around here, but the integral is certainly less than the sup. So I'm going to pull that out and take the sup for P of that likelihood ratio. Times, what am I left with? I'm left with just, if I take that out, there's only a 1 in here. So what am I getting? I'm getting just the prior probability of this set. Right? It's just 1 in here, so I'm just integrating the prior. In fact, let's go a step further. The prior probability, it's a probability, it's less than or equal to 1. So I'm just actually going to replace it by 1. And then I have the denominator. The denominator, I'm going to take actually e to the log of this. So this is e to the sum of the log of these. And actually, I'm going to put a minus here. Okay, I just took the log and then the e of that. And of course, the log of a product becomes the sum. And then I put a minus to flip the P0 on top. The nice thing about this proof, and actually the reason why I wanted to go through it, is it's going to use some elements of things we've done during things like concentration of measure. And believe it or not, we're pretty close to the end of the proof already. Because the first thing here, how would we bound this thing? Well, it turns out, and I'm going to skip a lot of technicalities, but I want to get the idea across. How do I compute? This is like a likelihood ratio. So this is like the likelihood function, essentially, over this set outside here. How can I bound the maximum of something? Well, one thing that we often did was to put a finite covering on things. This is a trick we've used often, right? We did this for minimax theory. We talked about this in concentration of measure. Is if I take some distance measure on these, densities, and I ask, what is the covering number? Remember, the covering number is the number of balls of size epsilon to cover the space. And let's assume that's finite. Then I can cover it, and I can approximate this supremum basically by like a union bound, like the number of these times how big the likelihood ratio can be at each of these points. And a simple kind of, an inequality similar to Hoeffding's inequality would say for one density, this goes to 0 exponentially quickly. It's not quite Hoeffding, but something like Hoeffding. And then there's n epsilon of them. So the top, using a kind of concentration argument, I'm omitting details, but I hope this makes intuitive sense, right? If I did a union bound over the balls and did an exponential inequality for each one of these, we're going to get something like e to the minus n epsilon squared times the number of these. And this is just some finite number. I hope that seems kind of believable. Of the balls to cover the space. And then we still have the denominator. That's the integral of this guy. Actually, let's look at this guy. This is a sum. It's converging to its expected value. In fact, let me put here e to the minus n1 over n. Okay. What is this average converging to? What's the expected value of that? This is 1 over n, the sum log p0 over p. That's just the KL, that's convergence. So this is basically e to the minus n times the KL divergence. There's a limiting argument going on here, but this is approximately the KL divergence between p0 and p.
So the summation of the distance has special form? The summation of the
No, this is an average. And so the average converges to the expected value of one of them. Yeah. There is an n out front, though. Yeah. So just carrying that over to the next board, what have I got? I've got that posterior probability is less than or equal to some number times something exponentially small, sort of a hoofing thing. And then approximately it's the KL distance between. The way to picture the denominator is, if I just drew it like the real line, we're computing the KL distance from p0. So that's some function like this. That's what we're integrating in the denominator. E to the minus n times this, actually. So in fact, if I restrict myself to let's say a ball and KL distance of size epsilon, that makes the denominator smaller. That makes the whole thing bigger. This is less than or equal to over the same thing. I'm just going to do it over, let's call it k delta. So I'm just restricting the integral now. That makes it bigger because I'm integrating over a smaller region. But now, the worst this can be in that ball is this delta squared. K is always less than or equal to delta. So this thing is bigger than or equal to e to the minus delta squared. So the ratio, in other words, is less than over e to the minus n delta squared. I'm pulling this out by making it at its biggest value. But what am I left with? I'm left with the prior probability of this Kullback-Leibler neighborhood. Because I pulled this out, and I should have said there's a d pi here. You see why the prior probability of a Kullback-Leibler neighborhood has to be positive. If this was 0, this would blow up. But if this is finite, this is just a number. If this is positive, this is just a number. And this was for arbitrary delta. I'm going to take delta squared to be epsilon squared over 2. Remember, I said it's positive for any delta. So if I take it to be epsilon squared over 2, this is e to the minus n epsilon squared over 2. So this is actually equal to, and this becomes epsilon squared over 2. I was able to do that because I had a positive number here, positive probability in any Kullback-Leibler neighborhood. What have I got? This is just some finite number. This is just some positive number. And this is going to 0.
Where did you use the Hellinger?
So good question. Where I snuck in the Hellinger was when I said that this soup I could approximate by this covering, and then each one of these would satisfy a kind of Hoofting-like thing. That's only true because each one of these is at least epsilon away in Hellinger distance. That's how I got this. I didn't show the step. But to show that the likelihood ratio of this thing between any density and the true density, so this is just a general fact. If you give me two densities, an arbitrary density, and I compare it to the true density, then with high probability, this is less than or equal to e to the minus epsilon squared, where as long as these are their Hellinger distances at least epsilon away. The proof of that is just a few lines long. It's very similar to Hoofting bound, but it's slightly different because it uses Hellinger distance. That's where I snuck in the Hellinger. Most of the modern stuff, so there's a lot of stuff in machine learning and statistics now about the behavior of non-parametric posteriors. Like people try to establish consistency and so on. This is basically how they do it. Just doing these kinds of steps. The top you bound with some sort of exponential inequality, and the bottom you bound usually using some sort of Kullback-Leibler argument.
Why did we need it, the delta thing to be true for all delta? We just need it for that particular epsilon over square root.
That's true, but so he asked, I chose delta to be this, so I actually only need this to be positive for that particular delta, right? But the claim, I didn't actually make the claim clear. I'm claiming that the posterior probability outside that ball goes to 0, but I'm claiming it's true for every epsilon. So I have to be able to do this for no matter what epsilon I choose. I'm going to have to do that. Yeah. No, this is a state. The statement is about epsilon. The delta only comes in as part of the proof. Yeah. So I think that's actually kind of revealing about the structure of non-parametric Bayesian inference. It's a kind of a useful construction to look at. All right, so I guess we're stuck with, unless there's a huge swelling of support for me here, that we're starting spring break on Thursday. Okay, all right. So have a good spring break. And when we come back from spring break, we're going to do the clustering, and then we're going to do graphical models. Okay? All right.